and others have discussed the maximum likelihood estimation for the generalized gamma distribution in a different but equivalent form. We consider X as the generalized gamma with alpha, lambda, and Xi all positive, and then we let X equal to the log, we let Y equal to the log X, then we can have the PDF of Y. And in this expression, U is equal to log lambda and B is equal to the 1 over Xi. And in 1946, Bartlett and Kendall shows that Y minus U over B has a log gamma distribution. When alpha going to infinity, the mean and the variance of W star become infinite. So we make a further transformation and consider the variance W, which is the square root of alpha times the W star minus log alpha, and with the parameter mu and the sigma, where mu is U plus B log alpha and the sigma is B over square root of alpha. Then we can have the PDF of W as follows. And for alpha going to infinity, it approaches the standard normal PDF. And here we will treat alpha as fixed, and then the maximum likelihood estimation for a sample W1 to Wn from the log generalized gamma distribution represented as above formula can be written as the following two forms to obtain the mu tilde and the sigma tilde.
And this is for fixed alpha, yes?
Yeah, like we treat the alpha as fixed. And in here, then when alpha going to infinity, then the mu tilde and the sigma tilde is just the same estimation as in the normal distribution. And the overall MLE for mu hat, sigma hat, and alpha hat is conveniently obtained by first maximizing the likelihood function L for several fixed alpha values, and then zeroing in on the value of alpha hat. So for a given alpha, the maximum likelihood of a log L that can be written as the previous equations, then obtain the mu tilde and the sigma tilde. And for log L maximum alpha for several alpha values, it will usually be possible to approximate alpha hat, and a few more calculations will give alpha hat more accurately. Since the distribution of W with alpha changes very little as alpha gets large, but rapidly as alpha approaches zero. It is often convenient to work with Q, which is alpha with power minus 1/2 instead of alpha. Then we can have the transformed parameters for mu, sigma, and Q instead of alpha, lambda, and Xi, and where Q can be negative. And then after introduce the two method of estimation, we did some examples for model fitting. The first example is for simulated reliability data with failure time from active PLC. Then in here, totally, we have 20 observations within 6 censored data. And we did the model fitting without the censored data and within the censored data. And in here, I will introduce the R package for Flix survival, which is a flexible parametric models for time to event data, including the generalized gamma, the generalized F, and the Rosten-Palmer spline model, and extensible to user-defined distributions. And in the flex-level regression phase, parametric models for time to event data may be right censored, left censored, or left truncated. And in here, the built-in parametric distributions has included the generalized gamma for us to use. And in this package, the estimation for generalized gamma is used by maximum likelihood estimation and with the form of mu, sigma, and q. And in here is the Figure plot for the MLE estimation. And in here, the yellow line is for the method of moment estimation we did by hand. And from the plot, we can see they are, for these two methods, they are pretty close. And then here is the exact value that we calculated for the using the moment estimation and the MLE. And from the form of alpha hat, lambda hat, and Cassie hat, we can see actually the value looks different. However,
let me ask a question. So here you give the moment estimate, right? MOM.
Yeah.
You also have the MLE.
Yeah.
So when you report these estimates, I would like to see the standard deviation. So we will see, is there any difference? You see what I mean?
But for moment estimation, we don't have standard deviation.
You do? Every estimate should have a standard deviation. Otherwise, the second movement is going to be infinity. Now, so I think that you should report this standard deviation. So if you report the standard deviation, what's the difference between the MOM and MLE? Did you understand my question?
Wait, do you want to show him the last slide?
Oh, you got the SD?
Well,
because there do have some questions to considering with the moment estimation and the MLE.
So show us the last slide.
well, I'm sure she will address it down the road. So let's continue. You made a very, very good point.
Thank you.
Thank you.
So should I show that open questions first or?
No, go ahead with this slide, with this particular model.
Okay. And in here, we show the difference in the form of alpha hat, lambda hat, and Cassie hat. However, in the form of mu hat, Cassie hat, and Q hat, we see these two type of estimation is pretty close. And then we plot the PDF of X for the two sets using the form of alpha hat, lambda hat, and Cassie hat. So although the value they are different in the plot of the PDF, they are pretty close. And then next, we do the model fitting with the sensor data. And in this function, they have already calculated for the sensor the data when using the MLE method. And they are really, they fitted really well. Then we also do the model fitting with moment estimation, but without any censored method. So we can say that it did not fit well. And in here is the value for the two method, although in here the moment estimation didn't consider the sensor data. And the next example is for the insurance data. In this insurance data is based on the 1 year vehicle insurance policies taken out in 2004 or 2005 and inside with our package, the insurance data. And for analysis, we use the data of claim amounts that exceed the deductible level of insurance $750. And here is the summary statistic for this data set. And here is the histogram of this insurance claim amount, where it's strongly right skewed, left skewed. And in here is the estimated parameter. We use the moment estimation. And this plot is for the histogram of insurance claim amount with fitted distribution.
So this data is real data.
Yes.
Okay. So this distribution is born for this insurance data because the fit so perfect.
And here is the empirical CDF of X, where the black line is data set, and for the red line is the fitted distribution. And we also try another insurance data that is pulled from the cargo and had been used in a national competition on the website containing 822 observations of insurance claim amount. And in here, from the histogram of insurance claim amount, we can see this data set is kind of symmetric. And we also use the moment estimation to estimate the generalized gamma distribution. And from the plot, we can see they also fit well. And here is the empirical CDF of X. And since the generalized gamma distribution can fit various data such as reliability data, the insurance data, traumatic brain injury lifetime data, and also based on the great flexibility of its generalized gamma distribution can fit various shapes of data such as right skew data, left skew data, symmetric data. And there also have some questions in the moment estimation and the MLE, like for asymptotic property of MLE can provide asymptotic confidence intervals or tests, but there is no comparing sampling distribution for moment estimation.
And what do you mean? No comparing sampling distribution of moment estimate. What's the meaning of this?
Like there is no.
You mean you have not yet to get the sampling asymptotic distribution or what?
So for moment estimation,
So what do you mean comparing sampling distribution? I mean, you have got the sampling distribution, or you have not yet to try to derive the asymptotic distribution of the moment estimate?
Not yet, and probably there is no any research for it.
You mean it seems that there is no sampling distribution, no asymptotic distribution, or you have not yet got it, right? You can get it, just moment estimate.
Like
just, yeah.
Till now, like there is no papers to show that here has any.
Remember, you you have the theory of general estimate equations. This moment estimate are solutions of these equations.
Yeah.
For GEE equations, you get asymptotic distribution. So this is a special situation of these GEE models. So if you go get it, and maybe the formula is very messy, but you get the formula, right? You agree?
Yes, but like for alpha hat, we got like as the numerical solution from that equations, and then we compared like for the GE equations for the lambda hat and the Cathay hat. So yeah, that is need to do in the following if we're doing this.
Yeah, you can do bootstrap, you can do resampling method, but you can also get this asymptotic distribution of the MLE and the MOM so that it can provide the standard deviation, because it is important when you report two types of estimates. We want to see the standard deviation. So you can see that what's going to happen if you provide the standard deviation, which is going to be bigger, the MME or the moment estimate.
Yes, and
think about it, okay?
Yeah, yes, that will be in later, because like for the bootstrapping, there are also in recent years they also like consider for bootstrapping for MLE method to construct the confidence interval for lambda for the mu and Cathay.
All right. For more bootstrap estimate, you can also bootstrap in the standard deviation. All right.
Yeah.
Okay.
Well, I think Dr. Peng is making a very, very good point. In any estimation, you want to know something about the sampling distribution of that, whether or not for finite n, small sample size, or for asymptotically. On the MLE side, there are no clear result besides those which are on the asymptotic MLE property, kind of to provide the asymptotic variance, asymptotic confidence interval, and so forth. On the moment estimators, there is really nothing. And perhaps because of those particular polygamma functions that are involved in that as a solution. This is definitely an interesting question that Dr. Peng is raising, and I hope Ms. Wang will consider that. But as of now, I think I've heard her saying there is no research on that, particular research on the moment, on the sampling distribution of the method of moment estimate. Let me add one more point. I think Ms. Wang did not, she mentions that in passing. Can you move to this slide on the reliability data?
With censored or without censored?
The data.
Okay.
So this is actually was pitched to, they came to us from this Aptiv PLC company. One of our previous students, David, what's his name? I forgot. Is working there, and he came in with this question. They have this type of data with censoring, how to model that. The traditional Weibull distribution did not seem to work well. Okay, and of course, naturally, there was a discussion about the generalized gamma. But this is really representing real life data in a small sample set. And Dr. Peng was again correct by saying that this distribution is perfect for fitting insurance data, because insurance data are notoriously skewed distribution, very much right skewed distribution to most part. And so there is a lot of flexibility here from a small sample of 20 to large sample of 4,000 or whatever. So that's I think the motivation.
I have a comment. So because you mentioned that the gamma distribution does not fit that well. So, Miss Wang, you should produce that estimation
Weibull distribution.
and draw
Weibull.
them in the same coordinate, so you can see the difference.
But again, so this is a difficulty to show in the following sense. There is a larger question here. So I have distribution 1, distribution 2, distribution 3, theoretical distribution. I estimate the parameter to the given set of data. And then I want to test which fits the data better, right? I can use a Kolmogorov-Smirnov-like test, but all of them are based on estimated parameters. So now, what are we comparing? Are we comparing the p-value of those 3 different tests of Kolmogorov-Smirnov? How can we rank the order of the discrepancy between of the Kolmogorov-Smirnov distance in relation to estimated distribution? I think it's an interesting problem.
That's a good question.
Okay.
This is one way to do it. There is another way. For example, you can calculate the AIC-BIC. So look at which AIC-BIC choose the best model. A third way, at least graphically, draw the histogram of the data. Draw the fitted curves.
But
by
remember,
eyes, you can see which will fit better.
Well, sure. And so if you'll show, Ms. Wang, can you show again this graph of the reliability with yellow or whatever, that one. So they seem to be, I'm looking at that and actually they're pretty good. Yellow and red are quite similar, but I cannot quantify that necessarily, right?
But but maybe we should look at the histogram. You get the data, draw the histogram, draw the fitted curve.
Remember, here is a 20 observations. This is what you have, or 14 observation. So the question, you are correct, but how do you measure that in various instances? How do you quantify closeness based on estimated paradigms?
So first method is you just mentioned, perform a test. Second, we can calculate the AIC, BIC. So,
but those are based on likelihood function, which is very shaky ground in this family of distribution.
So
right?
we draw a graph and let people have a look.
Sure. I like this picture. I like this is a good fit. Here is a good fit. So
there's another way. Draw the histogram, draw the fitted curve. So let's see which fit is better by our naked eyes.
Yes. So here it is. This picture.
This is the what? This is the density curve or what curve?
No. This is a survival function.
Okay.
This is basically the 1 minus capital A.
There's no difference in here.
Of course there is no. Yeah, of course but this is not on the center.
Maybe you draw the SD, the standard deviation curve. The memory may be better. Draw the curve with the SD to be the confidence band.
But those confidence band are basically here in this case are artifact of the asymptotic distribution of the presumed asymptotic distribution of the MLE.
That's right.
But this is 20 observations. Asymptotic distribution of the MLE in this case is really, it's really much to be, how should I say, to the eye of the beholder.
So we do a simulation. We simulate the data, choose the sample size bigger.
True, you can do simulation. But remember that business about, can you show this MLE and moment generating function, MOM side by side estimates? Ms. Wang?
To draw
the slide with the numerical result about the MLE.
This one?
Yeah, sure. You can see there are many possible numerical solutions that brings the same shape of distribution. So, Ms. Wang has a lot of things to think about, don't you?
Yes. Because in here, like alpha hat, lambda hat, and psi hat, it's different, like showing for the MOM and MLE.
So when you compare two estimates, the first method is just Dr. Boge mentioned. You can report the standard deviation. You can draw the curves, draw the histogram in the same coordinate. And you can run simulations to make comparison if you do not have large enough data set. So you can see that there are many things you can do to demonstrate that this distribution fits better, right?
But here is also saying like for MLE, we estimated as for the form of mu, sigma, and q. But for MOM, we have the form is for the alpha, lambda, and psi. For each time, the comparison for this method is like the two type of forms. So I'm not sure, like when we comparing in this different form for these two methods, then what will happen for this, like for like the standard deviation or something more?
It will happen. What will happen? I think it's the MLE is going to beat the MOM in efficiency. For other considerations, I don't know. Maybe. All right. So you compare them so that you can convince people, right? Your estimates, your distribution fits better.
Yeah, because like in here, that's recently they also have some research for the MLE, and they compare like for the penalized MLE and the profile likelihood to they compare these different methods to estimate the generalized gamma distribution, and they compare like for the standard deviations.
Okay. How many parameters do you have for this generalized distribution?
3.
Why you want to penalize the 3 parameters? What's the motivation for that? We can handle 3 parameters, okay? Even 30, we can do it. So we don't need to penalize any parameter. We get,
in
all
their research, they like to compare various methods, but are all related to the MLE.
Okay, maybe they have their reasons. You have not told us.
Yeah, like to drive which kind of MLE is the best to estimate the parameters.
Well, what kind of MLE do you have? You have the MLE, what other MLEs? You have a penalized MLE? You penalize what? Why you want to penalize? For what reasons?
Well, this is a paper, I think, that was published this year. Am I correct? Is that the paper you're mentioning, Ms. Wang?
Well, that one is for the paper that modeling for the traumatic brain injury in lifetime.
Oh, okay. Okay. That is a longer paper.
2019.
Yeah. Well, I think the part of this discussion is that there is no equivocal answer or satisfactory answer about the behavior of the MLE in this class, nor the moment estimator in this class. That I think it's my general sense. There is no one kind of authoritative reference that says, okay, here's what you do.
So, Ms. Wang, I also got a question for you now. Why you need to work with the MLE? Why you want a moment estimate? Why you want 2 type of estimate? So that at least if you give me 2 type of estimate, one of the 2 estimate, they should have some properties beat the other estimate. Otherwise, why you should use two estimates? For what reason? Like, my question is, what advantages for me to use the moment estimate? You have a nice formula, or you also solve the equations?
Like for the method of moments that we can like to solve from this numerical solution to obtain the alpha hat, and then we can have the Casey and the lambda. But like for the maximum likelihood, they do the first they do the transformation to have the mu, sigma, and q, and then they are like to try several alpha and then fix this alpha to calculate for the mu and the sigma.
Okay, I see. So you mean the moment estimate is easy
like
to compute,
more,
right?
Yeah, maybe more easy and accurate to have the alpha hat.
So I would do the following. I choose the moment estimate as the initial estimate. Then I get MLE. How do you think about this way? Use the moment estimate. They're not good enough in efficiency. So I'm improve is efficiency. Taking this moment estimates as initial estimates, plugging into the algorithm for computing the MLE. How do you think about this way, numerically?
Yes, then since from here we can have the alpha hat.
No. At least it's much easier.
Yeah.
You can get the much easier. It's much easier. So the moment estimate is a guide to the true parameter value. So you got the MLE, you got the efficient estimate, right? So that justify why, let's say, why we blame the moment estimate here. Otherwise you got, okay, it's easy to compute, right? Maybe you can try that way. Okay?
Yes.
Otherwise, like now you have enough computing power. So we're not that much bothered with this finding the MLE. So in my eyes, the MLE may be better, at least in theory. Right? So, but there is a problem with the MLE. I do not know where I find the MLE. You need the initial value of the parameters. So you can use the estimate, the moment estimate as initial value so that you can get the MLE, right?
So, Ms. Wang, do you think that Dr. Peng is correct or not?
Yes, because like we can use the moment estimation for the alpha hat, then the range to choose the alpha hat can be limited by the moment estimation.
That's a pretty good suggestion.
Thank you.
So actually there is a third estimation method not covered here. And we can refer to that in general terms as least square estimation. And because you have a closed form expression for the CDF. And actually all of them, all those numerically intensive procedures require some initial guessing, okay? Mm-hmm. And the moment estimator can always serve as the initial starting point for whatever numerical procedure you're invoking, whether or not for MLE or LSE or whatever you want. Part of the reason that we didn't hear much about this estimation method, or they have not been development since 1965, was basically that initially it was brushed off as difficult, computationally difficult method because of that solution of the polygamma function, which nowadays is not a problem whatsoever. It doesn't even take 5 seconds.
That's right.
So there is a lot to catch up in here, for sure.
I agree.
And here is a reference I used in this presentation. Yeah, thank you.
So let me ask you a final question.
Uh-huh.
If you ever to teach basic statistic course or probability course, would you prefer to teach the gamma distribution separately, the negative exponential distribution separately, or the log normal distribution separately? Or would you allow yourself to teach also this generalized gamma?
The generalized gamma, because it can and from the generalized gamma to derive the gamma distribution, Weibull distribution, and anything. So like to have a systematic introduction for the gamma distribution.
What you're holding in hand, Sean? What is that?
You know that signal. You see this here?
I have no idea.
Memphis. The signal in Memphis. Presley.
Oh, gotcha. Gotcha.
Avis.
Any other questions?
So Hong Lang, how did she do on time? She was very concerned about that.
Do you mean for the time of the presentation?
Yeah, did she use too less of a time, adequate time?
I guess it's good because but we have a lot of discussion. I mean, that's very good. Yeah. By the way, Dr. Booker, are you happy with Jiayu's answer to your question, the last question?
Well, I think regarding the teaching aspect, I think I will appreciate other input from everybody else. I think, it struck me that we really never mentioned that in our basic courses. Mentions this distribution.
So I want to use this distribution, if I want to interrupt, to show people that normal distribution is not the only distribution. There are many data. The normal distribution do not work, okay?
So for example, after like 519 or 516 for the probability, when we started to teach the statistics part, we will review the probability part. Usually we will summarize kind of all the distributions you learned from the 516 or 519 to be the so-called exponential family, right? We only use exponential family kind of to that's the umbrella to include a lot of different distributions. And here, I guess we can also use this, generalized gamma distribution to include a lot of also distribution into this family. But of course, when I learned this part in my PhD study, we also learned that the location scale family, right? Location scale family, exponential family, those are two bigger families for the distributions. And I guess here it's also good to, to use this. I don't know whether I think it's good to have this generalized gamma distribution to include all, so much.
Well, Hong Lan, you're absolutely correct about the exponential family because it admits natural statistic, natural presentation, cumulant generating function, and all those statistical problems. However, in real life, this generalized gamma is neither this nor the other. It has two shape parameters that gives it that flexibility and one scale parameter. And of course, you can do a truncation. You can shift it from instead of starting at 0, you can shift it anywhere you want. Right? So you can make a fourth parameter there.
Yeah,
But
of course, that's the essence of this new family of distribution. Like that's I also want like Jiayu to kind of show, for example, one example. If we only use a standard gamma distribution, only have two parameters, why it's not enough to model some reality. And what's usually, for example, empirically, if you see some particular feature from a data, then you should think about this third parameter, C. I mean, if we can get some guidance from the talk, then I guess that would be motivate other people to use this distribution, right? Otherwise, people will think if I only use two parameter gamma distribution, can I already have a very good approximate to a lot of the real case or not? If that's the case, I'm just going to stay with two parameter gamma distribution, right? So for the moment, I even don't know, like in which case I need to use this one, right?
In broad stroke, I'll make the advocacy that if C is positive, that will be a very good way to model some kind of left skew distributions. Okay? If C is negative, that would be appropriate to model largely right skew distribution. Okay? And anything in between. So you have some general guidance here. For example, the log normal distribution will be right skewed, right? Naturally, depending on, but you will never be able to model left skewed distribution with log normal distribution. So it's inappropriate. So there are many instances like that. As Sean said, the normal distribution is not the solution for every possible shape. So that's, I think that is a point.
So in the existing literature, there are a lot of applications using this distribution now.
There are a lot of people who are trying to use it, demonstrating its flexibility and getting hung on the essentially lack of bona fide, classified statistical properties as we are familiar from the usual, the usual part. You need to do all sorts of weird transformation to get to some MLE property, asymptotic MLE property. So
it's still under the theoretical development stage. It's not used a lot in practice yet.
Yeah, but I'm not sure. Yeah. There has been some gap here, right, from 1965 and the 70s and stuff like that. So I'm not sure what's going on myself. I'm not.
Okay. Yeah. Any other questions from the audience?
So my last comments. I got a very bad impression. It's just maybe me. It seems to me
what? Please, can you repeat? I'm sorry.
Very bad impression about the distributions. It seems to us statistics have two field distributions we can use. Maybe it's just my bad impression. Okay, my wrong impression. You see that you got only field distributions. I think we should have endless distributions for us to choose, not just a few.
Well, where do you see few?
Count how many? Normal, binomial, Poisson.
Oh, in general, you're saying. No, this is the curse of the exponential family of distribution.
Exponential family just a few distributions. Poisson,
yes.
binomial,
yes.
normal.
Yes, this is what I'm saying. This is the curse of the exponential family of distribution. It was easy to convey that we have a class that has the similar properties in general, okay? In respect to some measure, dominating measure, whatever it is. But, and then there was a movement about stable law and other things. I mean, there are a lot of other distributions that are available. Some of them are tractable. Some of them can be written as infinite sums and whatever they are, but they exist, of course.
Maybe you should blame central limit theorem because finally it goes to normal, right?
Everything goes to normal, right?
Yeah.
If you appropriately normalized, if you have enough sample, Otherwise, we only need one distribution, normal. Okay? You don't have enough observation.
No, you just need coin toss. Just coin toss. That's good enough.
Okay. Okay.
Yeah. Okay. So I guess it's a good time to stop here. Okay. So we will have the last seminar next week and given by Dabolina. Yeah. Bye-bye. Bye-bye.
Thank you,
Ben, do you have
Jayu.
something to say?
Thank you.
Thank you. Bye.
Okay.